world. Of course, later, I mean, but this is still a little bit ideal, right? I know Z, I know X. Sometimes you don't observe the Z. You only see Z independently, right? Observe even the state of you try to estimate it. It's actually hidden from you, right? So for example, Z is a dynamic process that evolves on its own, takes some input, influenced by some input, and evolve on its own. This is actually a dynamic system, linear dynamic system, 对不对？学过控制的人或者学过信号处理的人应该知道这类系统很简单的这个时间time series but you don't know Z directly. You only see Z through some projection, multiply Z, 知道吧？好 ，now the question is how can I through X? How can I estimate Z through sequence of X I observed? 而且 how to estimate Z only use X I observed so far, 对吧？就是这个问题是个 causal 的 denoising problem。我只用我过去的观测值来预测将来的 Z， 同时对现有的目前看到的 Z 去造 denoise。Okay, that's a question. Right. This is a question started by Kahneman 为什么是1960？ Kahneman actually derived a closed form formula for this problem, right? It's known as Kahneman filter, right? It takes this form. You know, Z hat is estimated Z and AZ hat plus from the previous instance, and you solve this recursively. And also you look at the prediction from the previous state Z, CZ, with the current observation Xn, you take the difference, this is error terms, and there is a gain called the Kahneman gain. You multiply a matrix, you derived, right here, there's a formula associated with it, and you multiply this error with the K. This is actually more like a feedback using this error term to predict what the next state should be. 非常干净漂亮的一个这个 filter 一个 causal filter 非常漂亮的一个 filter actually, Kahneman filter is the reason 为什么大家知道为什么美国最先上了月球，对不对？很大程度上是因为卡尔曼滤波的功劳，对。因为 1960大家都不是在这个都想去这个苏联和美国不是在竞争嘛，谁先能登月球？所以同学们，这就是一个很有趣的一个故事啊。为什么 fundamental 的技术才是真正的了不起的？ OK， 会 make a huge difference。对，60年代实际上是在苏联和美国的竞争这个太空竞争的时候，对吧？实际上是苏联人最早是领先的，因为苏联的控制理论是远远超过西方的。The control theory, the dynamic systems, the Russia is much ahead of American. 西方国家的，但是卡尔曼滤波改变了这件事情。卡尔曼的目的是就是说，但是你做 feedback， 对不对 ？If you want to have feedback, you need to know what the state is. 你要去控制一个飞机的状态或者航天飞机状态，你得知道它的状态，内部的状态是什么。但你只通过一些 sensor 看到它的间接的信息，对不对？你如果通过这些间接的信息 estimate 你的比如说飞船的这个正确的姿态，这就是一个感知的问题 ，estimation 状态空间 estimation 的问题。卡尔曼滤波正确的解决了这个问题，而且非常快。非常漂亮所以让我们的即使你的控制器不是那么好，但是你只要你的状态 estimate 很准，那么你的整体系统的效果，整个闭环系统的效果会很好。所以卡尔曼滤波实际上是给了这个美国的这个航空航天很大的一个 leverage 这是 Russia 一直没有的，他们的这个 estimation 一直做的比较 clumsy， 花很多的代价很多的时间去做这个事情。Computation extremely taking a long time， 所以你可以看到，对吧？一个真正的 fundamental 的东西，看似好像很简单，而且这件事情 this thing is actually conceptually again is this problem. Okay, it's a special type of problem of this kind. Okay. Now this is a Kahneman filter, right? Now, I mean, for so far, all the problem you can see is similar, is that I have some data, right? I have some observation. I also have some samples A. I try to regress. I know A, I know Y. I want to solve X. 对不对? This is the same time, only under different condition. X is sparse, or it has X has to be causal, and so on. The function of time, so on and so forth. It's just a special version of this. 啊，对吧？所以也很简单。你看这么多人工作解的问题都一样啊，只是它的 setting step 的简单还是难啊？那个漂亮不漂亮啊？还是跟它的那个条件有关。But everybody requires what? In order to build the Kalman filter, right? If you know here, this form, Kalman filter, for example, you need to know A, B, C. Also, you need to be to compute K, right? The matrix K actually depends on A, B, C. So what if I don't know A, B, C? Right? In order to build this Kalman filter, also in order to even to solve this problem, right? Y and A are given to you. See, even Y and A got given to me, the problem can be NP hard. Right, I told you. 就是你就是知道 Y 和 A 这个问题都可以是很难的，还别说如果我不知道 A 呢 ？The question is, what if I don't know A? What if ABC is a black box? I only know the input output. 所以大家不是喜欢 black box 吗？现在，对吧？ A lot of people these days says, "Oh, we don't need to know the black box." No, we need to know, right? See, in 1960s, people want to know. 就是你可以弄一个 language model, you probably don't care. 但是航天飞机呢，动不动就爆炸，对不对？啊，你能不知道吗？对，所以你看，当时卡尔尼波也好，对吧？航天竞争的时候，一是要 estimate 状态，当 ABC 知道的时候要知道状态。You want to estimate the state correctly, and also what if you don't know ABC? You have to also estimate. So the next steps of Kalman filter is how do you estimate ABCD from the input output? Given that the input output follow this kind of models, this linear dynamical models, how do you identify the matrix ABCD? Right? 这是什么问题啊？ This is called a system ID problem. 啊，要去辨识这个系统，我要知道这些内部的参数啊，这个黑盒子的 ABCD 是什么啊 ？Sounds familiar？ 听起来比较熟悉吧？你看，几十年前人家在做简单模型的时候都知道，任何一个黑盒子一定要打开的，对不对？要想把这件事情做对、做好、做高效，这个盒子是一定要打开的。所以现在有些人说一些话是极其不负责任啊，甚至是反科学的啊。但是现在就是这个社会，同学们啊 ，put that in perspective 啊。关键是你是不是 serious 啊 ？Try to understand 啊 ，try to get this done correctly 对啊。好 ，How do we do this？ 大家好好去看一下啊，90年代啊，大家去翻一翻90年代啊 ，Hinton 有好几篇文章在做 EM algorithm， 他在解什么问题？他就是在解系统辨识的问题 ，OK？ 包括 backpropagation， 他都在做这个问题，啊，对，所以只有这些跟着别人屁股后面什么都不知道的人啊，才觉得这个跟上去一知半解就行了啊。真正聪明的人都知道问题的关键在哪里，重要的问题是什么啊？该做的事情是什么？对。So this is actually system ID. Actually, in linear system, there's a lot of people work on it, right? So as I said, how do I identify ABCD? It turns out it's actually very so. See, this is a linear system, right? Remember, everything is linear here, right? Linear operator, linear systems. Hence, the key to that's a whole industry. I don't want to get into details there. If you're interested, I'll give you a reference. But conceptually, since everything is linear here, so hence that to identify ABCD actually relies on the fact this is linear. So to the actual solution is it turns out to be very conceptually simple, right? So if you build a matrix, so-called Hankel matrix, very much take segments of the input output, right? Build them as columns. Take a finite segments from U and Y input output, right? Build a so-called Hankel matrix. Then, though you compute their correlation, 这个 Y 和 input 和 output 的 correlation turns out that correlation matrix is always has a finite dimension. The dimension is always, doesn't matter how long you take the sequence. This matrix is always had a rank less than equal to the intrinsic dimension of the dynamics, 就是 x 状态空间的维度。Right? So the dynamics, what is the intrinsic degree of freedom the system has? So it doesn't matter how long you observe the system, right? The sequence turns out that it always lies on a low-dimensional subspace. 就是说，你的观测值啊，就相当于 whatever you observed always lies on an n-dimensional subspace. So once you get hold of that subspace, you can recover A, B, C, D from that subspace. That's essentially the idea from all linear system identification algorithm. Of course, later people extend this to nonlinear systems, so that actually leads to the discovery of the construction of the recursive neural networks. 这所以 RNN 怎么来的？实际上都是从系统辨识来的，好吧，同学们。所以任何事情啊，不要 take it the surface value。人家这么说啊，就我学了 RNN 就这样了，那为什么呢？它从哪儿来的？为什么要这样子呢？对吧？它是什么东西的 generalization？ 大家搞清楚，好吧？ Okay, now leads to the problem, right? See, this is the difference. The left-hand side is the linear regressor, right? I know the A, Y. I'm trying to regress, find a linear function to regress Y, right? To get rid of the noise, errors, right? So the regressor A is given, right? 比如说我要写成，对吧 ？Y 写成 U1 to UD，U1 to UD is given. I only have to find the coefficient. Now, the problem is that if I don't know the system, right? I don't know ABCD, I don't know the regressor, then I only know my observations lies on the low dimensional subspace, but I don't know where it is. I have to identify this subspace. So this is called principal component analysis, which means in mathematical term, right? So in order, you only have Y. You don't know the basis of the subspace U1 to UN. You don't know the regressor. Also, you don't know the coefficient associated with each Y. What you only given is a whole bunch of Y's, right? You give a lot of bunch of Y's. The Y's always lies on some low-dimensional, concentrate on some low-dimensional subspaces. But you don't know the basis of the subspace. You don't know for each point. You don't know the coordinates of that function, of that sample inside that subspace. You don't know the W's either. So you want to estimate the set of bases and the coefficient for each of the observations such that the expected variance of the residual is minimized. 也是做 least square fitting, 对吧？所以你看这个问题啊，跟前面的问题 different. What's different here? Here, Y and A are given to you. Sorry, shoot. You know Y and A, right? Here, you only have Y. You try to estimate both U and W, right? In the regression, you know Y and U. You try to find W, but here you have a bilinear problem, right? It's a much harder problem, and also called the principal component analysis. People started investigating this problem about 100 years ago, right? Pearson and Hotelling. This is a classical problem in statistics called the principal component analysis, right? Probably how to find the subspace. Now, so you can reformulate the problem, right? Since this is expectation, basically for many observation Y, you want to estimate U and common U and different W associated with each Y. So basically, you try to, given a matrix of samples, you try to estimate the U and W together, right? And this problem has a pure algebraic interpretation, 对吧？假设我不是在做 regression, if I'm not doing this kind of least square fitting, this kind of least variance type of setting, I just cast this as a matrix. Y is just, I have n samples, right? Y is m dimensional. Those are just columns. This is just a matrix. How can I approximate this y, since I know, right, y only is a linear combination of d, let's say, components. D is highly smaller than m, the dimension of y. So hence, I'd be able to, if I can write down in this form, right, every y as this form, so it only has d components, right? 所以它的 rank 应该把这个 epsilon 去掉之后 after I get rid of epsilon, the remaining should have be the rank d. So hence, I must exist a matrix of rank d that is very close to y, right? So I try to approximate y with a low rank matrix of rank low more than d, right? 这叫 low rank matrix approximation problem. 大家现在玩神经网络，知道训练一个大模型完了以后，大家有一个post process 的步骤叫什么 ？LoRa。大家知道 LoRa 在干什么 ？Anyone knows? So after you train a very humongous matrix, pre-train, right, a big model, trillions of parameters, and then usually once you're done, you do another post processing, right? Very crucial, both in terms of reduce the parameter of the compress the network, as well as it turns out it can also improve the performance. The procedure called LoRa, 对不对？非常 Anyone knows what the LoRa stands for? Anyone? Audience, you can unmute yourself and answer. LoRa is exactly stands for low rank approximation, right? Each layer, the operator is a matrix, and you approximate that operator with a low rank matrix. That will reduce the number of parameters, and also turns out if you do that, you actually can improve the overall performance. Very surprising. That's why it become a standard step, even to post-processing the trained neural networks. Everybody does that, right? Not only you get a more compact network, but also you get a better performance. So see, this problem has been, actually this turns out the algebraic, there's another formulation by Pastrami and Jordan, right? Jordan form, in linear algebra, you should know, right? This is the same Jordan, right? Very famous Jordan form, 1870s. Already says, if I give a matrix, how can I approximate it with up to d factors, so that find the best rank d approximator, right? By a sum of those rank 1 factors. Using d factors to approximate y. So it turns out that this problem has a very beautiful solution, right? 同学们，叫做 SVD singular value decomposition。我们下节课可能还再 review 一下，所以你们现在赶快是先读啊，不要等到我讲你们才。你们在研究生 in graduate school you have to read first, then take the lecture, right? 不是等完 lecture 以后你再去读 ，OK? That's already too late. So the SVD, right, singular value decomposition, basically you take a matrix, I can always decompose into 3 matrices. Sigma is a diagonal matrix, U and V are orthogonal matrix, right? Have this the standard form called SVD. 大家都知道 eigenvalue decomposition, 对不对？特征值分解，但特征值分解是对正交正 ，sorry， 是对方正，对吧？ The square matrix, you have the eigenvalue decomposition, but also not all the eigenvalue decomposition is real and so on and so forth. If you want to get the real matrix, it has to be the function, the square matrix has to be symmetric and everything, right? But SVD is not. SVD actually has applied to any rectangular matrix. 任何矩阵就是可以是方的，可以是不方的可以是那个长方形的矩阵都 have this kind of factorization, right? And if you just take the first d components of the singular value, the leading singular vectors, right? Take the singular vectors with the largest singular values. Turns out that's the best rank d approximator to the matrix Y. Right? So you give an optimal solution to the low rank matrix optimization problem. Turns out this is probably the only case. Low rank approximation turns out in general, just like the sparse recovery problem, right? In general, it's NP hard, but in this setting, only for this problem has a closed form solution, has a computable solution. So if you change the setting a little bit, the low-rank matrix approximation very often becomes a NP-hard problem. OK， 但这个 setting 是一个非常 special case。所以这个 singular I cannot overemphasize the importance of singular value decomposition， 好吧，同学们对，如果反正我讲给大家如果只有一件事情你记得住，你这辈子只用记住一件事情关于线性代数，那就是奇异值分解。OK， 其他可以全部忘掉。Right? This is how important it is. In fact, at Berkeley, undergraduate student courses, there's at least the singular value decomposition or PCA will be taught at 5-6 different times, right? In different courses, statistics, signal processing, control, and everywhere. Okay, if you're not familiar with it, it becomes something you know everything about it. PCA SVD, right? It's one of the very few topic has a beautiful algebraic, statistical, and geometric interpretation. Okay? In each case, it's fundamental. And also, I can assure you, 对吧？对，在神经网络主宰这个地球之前现在的计算中心大家都在训练神经网络我不说嘛，神经网络最后也要走上 LoRa， 对不对？也要算 SVD。尤其在2012年以前，在这个 GPU 算大模型之前 ，before the deep networks, probably I don't know the statistics now, but we can do before the deep network, GPU computing deep networks or back propagations. All computers on Earth, I mean all computers on Earth, majority of the computation, scientific computation, right? 不管是做 nuclear simulation、life simulation， 所有的图像处理、信号处理，所有的这个仿真核物理、仿真各种流体力学、仿真做任何的科学物理实验，好吧？80%以上的计算机的时间是花在计算 SVD 上的。Okay, anytime you compute any linear solutions, linear equations, spend on this. This is how important it is. There are still teams of engineers in Google. The whole page rank, right, relies on the PCA. The search engine is built upon how to solve SVD. Okay, there's still a team at Google dedicated to how to speed up computing PCA, SVD. That's how important it is. So if any of you can improve the efficiency of computing SVD by just like 10%, you will become a billionaire. Okay? So that's how important it is. So PCA, okay? Now, while there's something, the PCA essentially assuming what? Your data lies on a low-dimensional subspace, right? D-dimensional subspace, basically. You try to fit your data. Why? All the points, vectors, are concentrated around the D-dimensional subspace. You try to identify the subspace and find the coordinates of each y. That's essentially what you're doing. Okay. Now, that's a picture on the left. 对吧？左边那个图你看，主要的都是 concentrate on this direction 反正其他的方向可能就是噪声了，就是这个 E 了对不对？Get rid of it, right? Try to find it. But there's a problem, right? Sometimes my data is not as just has a single mode, 对不对？我数据不一定就在一个子空间right? For example, what's on the left, right? If my data, even 你看在这个即使在二维，对不对？二维空间我数据如果有两个模态，there's two mode, right? See, this is already looks like if I fit a PCA, then basically PCA will give me this direction, right? This is the most direction I fit a subspace to it, right? This is the most the energy has the largest, highest singular value, and this is the second singular value, right? PCA is going to remove. Think about this direction are all noise, errors, and this I just project all the points onto this 这条长轴这个方向上，知道吗？ That's obviously lose some structure, right? 因为你看嘛，这个数据明显的有两个模态嘛，对吧？There's actually two model. Hence, there's some limitation about PCA. If you just model your data with a single linear subspace, it's always a limitation, right? So people try to see, oh, maybe how do I make this slightly more flexible, right? So Anne, Herald, and Newton, 1985, proposed maybe I should fit multiple modes to it 啊，这叫做把这个 x linear superposition of multiple independent components, and they are somehow restricted, right, to each other, right? It's not like a single mode. Right? This is called ICA, independent component analysis. I cannot also, this is also a very fundamental model. Okay, 同学们. Why this is important? Actually, if you read the original paper, 1985, ICA is first proposed. The objective is try to as a simple model for our memory. Right? The people actually believe, right? We memorize different things around the different prototypes. Right? It's an early model for our neural memory. A 1985 paper suggests this is a model for our memory. By the way, in the 1990s, of course, this is a proposal about the 1990s, the Orja and the Havarinen, those are the two Finnish guys, made a lot of progress. They dedicated to study this problem. In fact, in late 1990s, those two guys are the ones justify why in neural networks you need the nonlinear activation function. Precisely because if you try to solve a lot of least square estimation problem, you try to solve ICA problem, then you need the nonlinear activation functions. They're the one to justify why, theoretically, why neural networks works, right? So people like Hinton, and including Jan LeCun, they are just practiced very heuristically, but Orja and Havarinen are the ones actually really working on the theoretical justification for the architectures of nonlinear networks, right? In my opinion, they actually deserve the Turing Award. Let alone, right? The score function was proposed by Apple, Havarinen. Yeah, he's actually, if you look at his paper, right? He proposed, why he proposed score function, we'll talk about that later, is precisely try to solve the ICA problem, okay? Guys， 所以我们今天用的这些 diffusion model、denoising model， 对不对？大家这个觉得自己很理解啊？为什么 ？Why? Where did it come from? Right? So those two guys you guys should remember their names because in my mind they are the heroes, hidden heroes. Really made a fundamental contribution to our understanding of low-dimensional structures, and also they propose the fast algorithms. They're the first to generalize the power iteration for solving PCA. I will talk about that later, right? Next chapter. So how to solve ICA very efficiently, right? In fact, the first for PCA, we'll talk about this later. Havarinen the contribution 真不得了啊。The PCA, we all know right now we solve the neural networks, right? We do end-to-end backpropagation, right? The only case that you don't need to do a backpropagation, you can do local updates. Precisely working as a neurons to solve is a PCA problem. And the first algorithm, again, is given by Havarinen or Jia, those two guys. They actually showed that you can use precisely like a local updates like our brain to compute as an algorithm. You don't need a backpropagation. You can do something precise like our Herbian connection between our brains, neurons, to solve the PCA problem. But for any other, only the PCA so far. But the ICA or any other algorithms, any other low-dimensional structures, people don't know. There's no such algorithm. Everybody still relies on end-to-end backpropagation. Okay, but they are the first to show in 1980s. The PCA you actually can solve using a truly like neural networks. The updates looks like our neural networks, like our brain. We'll talk about that later in later chapters. Right, of course, later on, this kind of early model still very idealistic. So in around 2000, as I said, about 10 years ago, Renee and I work on the image segmentation problems and high-dimensional data problems. We realized that a lot of high-dimensional data are distributed around the mixture of low-dimensional subspaces. Very general, flexible models, right? Low-dimensional subspace or Gaussians, possibly with noise, outliers, and those subspace may have different dimensions. We call them generalized PCA problems, right? So there's an entire book about it. So this is also the work make me realize the importance of low-dimensional structures, right? Although at the time, the solution primarily based on algebra and some global optimization. But nevertheless, that's the time when I realized that the importance of low-dimensional structures are important. Hence, sparse structures, low-rank structures, and so on. They're all related. ICA structure, they're all study exactly the same class, assuming your data lies in a mixture of linear models. Okay. And of course, another general, so this gets me to, after the book, I start to get really into the sparse representation, right? To study more special cases. The diction learning is one special case of this, assuming it's kind of unified model. The complete or over-completed diction learning problem is, think about this kind of is a generalization or unification for the GPCA problem and the ICA problem, okay? So you can cast those problems as a sort of a diction learning problem. Basically, you're only given a data matrix. You try to find a dictionary, a dictionary. By complete dictionary, we mean it's a square matrix, but we'll talk about the more general case later, right? You try to learn a dictionary. You don't know D, but you try to learn a dictionary such that all your data has a very sparse interpretation, superposition of it against this dictionary. So Z is a very sparse coefficient, which means every data, every column is X, you can write it down as a very few columns, linear combination or linear superposition of the few columns of D. 就是每个 X 数据，你都可以写成这个字典里面的最少的几个列的线性叠加，对吧？就这个问题 ，very sparse coefficient. D is a dictionary. 就学一个编码。It's called a diction learning problem. Of course, this problem in general, again, is NP hard, everything, so on, but again, turns out under very banal condition, it has very, very efficient solutions, right? It's very, very sparse. So the boundary between NP hard and tractable is quite interesting. Yeah. So you can actually make this very, very mathematical. And so it turns out this problem can be converted to, you only have to assume D is orthogonal matrix. So it makes the things easier to deal with. Do some preconditioning, pre-processing of the data. And you actually can convert this problem to the case that as if your data is generated by some orthogonal matrix and with sparse components. So those are the history. We'll get to this in chapter 2, okay? Basically, those are all the classical, assuming your data lies on a mixture of low-dimensional subspaces, basically, right? Essentially, it's making this assumption, your data, and then your job is to identify those subspaces, those spaces, and also express your data and as a sparse combination. The data, which subspace it belongs to, and only use the basis of each subspace to representing those data points, 对吧？比如说，就找到S3的 G， 对不对？那么所有在这个 S3上的这些绿色的点，它的坐标只有一个，对不对？一个非零，其他都是零，对不对？好，或者是黑色的都在这个平面上，那就只有2个 G 是非零，那么其他都是零，明白吗？对吧？ That's actually what the problem is. But you only have, the hard part is you only have those data. They may have noise, they may have outliers. You don't know how many subspaces there is. You don't know the dimension of each subspace. You don't know the basis of each subspace. Your job is to find all of them by solving the D and Z. Understand? 所以我们下一章第2章，但这些都是经典的analytical model， 你可以认为他们的难度他们的 solution we're going to survey next time. Well, there's more to go, right? But in reality, right? I mean, my distribution may not be like this, right, guys? 对吧，同学们，对吧？如果不是这些 piecewise 线性、piecewise 高斯的，那怎么办呢？ Right? 比如说我们的 universe, right? Maybe there are like some Chalabi Yao manifold, maybe 10-dimensional manifolds like this, 对吧？对吧 ？Weird, 对吧？就是 x 零可能是 a random variable with probability density function, right? PA maybe concentrated on some 这个 P 它的 support 可能是这样的，对不对 ？Maybe looks like this, maybe PO looks like this, the support looks like this. Then if we, of course, we take some noise observation, right, it looks like this, x0 is clean, but there's some noise, R observation, and how do I know? Also, I only have finite samples. How in the world I can get hold of the clean data, right? Find where the subspace, where the manifold is, right? Where the true support of the density function is, right? So it turns out, amazingly, see, the problem is that I don't know analytic form. 我没法把它写成一组机，对不对？线性叠加什么 regressor， 对吧？I don't know that, right? So x0 can be very weird, right? The distribution, right? Turns out you still can do denoising. 你看前面我们要做 denoising 要怎么弄，对吧？ We have to find those spaces, right? Then get rid of the e, right? We do linear regression, right? We get a hold of, right? We remove the epsilon by identify those u, w, and we get off those epsilon, right? I have to find those subspace, then project my data points onto the subspace so I can get rid of the epsilon. Remember? The regression is there. I regress to the, now remove the error against those regressors, right? Just write down my value as a linear function of those regressors and get rid of the epsilon, the residual, right? But in this case, I don't have those regressors. I don't have those subspaces. How do I do? I don't even have an analytic form. Turns the main thing is you don't have to, right? Turns out if your job is just try to denoise against the manifold, the support, there is something known as Tweedy's formula. This is actually 1950s. Tweedy is the first to suggest that in order to find, if you only have your observation y, you want to denoise it against x0, minimize the mean square error, right? And your only job is to do is that this actually can be taken. You don't need to know the ground truth, PO. You only need to know what the noisy data distributed, the probability density of the noisy data. You only need to know the distribution of the noisy data, which is what you have. Then do a gradient descent against the density. Then that actually gives you an optimal estimator of the denoised estimation of the ground truth x0, right? This is amazing because you can actually do denoising without even know the support of your distribution. And this is true for general, including the linear ones. This is called, hence you only need to know the distribution of x, which is from the sample. Hence that's why this is also called the empirical Bayesian denoising. You only need to know the empirical distribution of x. You don't need to know the analytic expression of the ground truth. You don't need to estimate that. Analytic model for P0. You only need to know the empirical, start with the probability density function of the empirical observations. And you can already do the denoising. Right? So we all know, right? Just to survey a little bit. We can take a break in 2 minutes, so we can resume. Right? I'll finish what are the Tweedy's formula's implications are, right? So we know if any data, clean data, I add noise to it, I get a new distribution, right? If I add the T is the scale of the noise, right? The variance of the noise, I add some noise. The larger the T, the more noise I add to it, right? So it turns out under natural technical assumption, the entropy of the process will always increase if you add noise to it. You can actually prove this. This is in Appendix B. You can read that later, don't worry. So basically, I mean, intuitively, this is simple, right? So this is my original distribution. I add noise. The more noise added to it, the data gets more dispersed and the entropy gets higher, okay? Yeah. But what if I do denoising? If I follow, right? If I had from a higher noise one, I try to find what is the noise reduced by S, right? T is the amount of noise, right? T is large. What is, I add a little bit less noise, T minus S. So it turns out you actually can estimate what if you reduce the noise by S, what would be that data looks like? It's called the denoise a little bit by S. So you only have to follow the gradient of the empirical distribution of the distribution at the time T with the amount of noise T, and scale this down by ST, and that gives you the optimal estimator for what the XT minus S would be, right? So that means since you can denoise a little bit by the amount of S. If you do this, the entropy of the process, you can prove actually the entropy of the process decrease, guys. All right? And if you keep doing this, as we showed in the book, right, you actually can get something like this. We'll talk about that later, right? Turns out this is exactly, right, what all the modern image generation is trying to do, right? If you have a lot of samples on the natural images, right? You start with very random noise, you actually train those denoisers. And step by step, you actually can converge from a random distribution, converge on the distribution of natural images, making the images look increasingly clear and more natural, okay? That's what really all the image denoising or image generator is doing these days, right? Okay.